All right, so welcome everyone. We are now in week 12. This is Thursday.
11.
I think this is week 12.
I'm so confused. I think it is 12.
You said week
It is
12 in
12.
your Monday, Wednesday class, so I
Yeah,
think
this is week
It's
12.
12. It's
We
12.
have 3 weeks from today is the last day of the semester. Oh my God. So yes, this is week 12.
That's crazy.
And I wasn't here last time. We didn't have class. We missed the section on regression. I recorded it and only one person bothered to watch it and utilize all of my time and energy and my work for for you guys, but that's okay. I'm not salty in any way. It's just the way
Hey,
it is. So
you know, we'll go back and watch it. You don't have to do it again.
no, it's too late. It's too late. Now we're here. So, but I'm just kidding. I'm not really angry. I actually it didn't take any energy because I was teaching that class. So last chapter was on correlation, was on whether or not two variables are connected in some way. This one is on what's called regression. Okay. Once you've established that two variables are linearly connected, the next thing that we have to do is we have to come up with the equation of the best fit line. There are ways of doing this that require calculus. We do not have calculus at our disposal in this class. It's not a prerequisite for the class. So therefore, you will not be given the formulas for finding the equation of the best fit line. However, we're going to examine some of its properties, and we are going to try to understand what makes it the best fit line as opposed to any other line that you might create. So for example, this line here looks pretty good, but how do I know that this line is better than that line, which is really, really similar to it? How do I know that the first one is better than the second one? What makes it better? So we're going to learn exactly what makes one line better than another, but we're not going to follow through to the end to understand how to find it. Okay, that we're going to allow calculators and computers and those who know calculus, so the better people in life, we're going to let them do it instead. Okay, so first, what is the line for? At the end of the day, the line is there to make predictions. Okay, I have all of these data points. These are actual people or whatever the individuals are under study. Those are the actual data that I'm using to find this best fit line. But if I had someone who, let's say, or an individual that landed at 42, in this case, centimeters, and I said, what do I think their height would be? The best thing that I can use is the line. The line says that, oh, you're at 42, then you're probably about 163 centimeters tall, because that's what my best fit line predicts that someone at 42 would be. Does everything fall on the line? No, of course not. I look at all the data points. Almost none of them fall on the line. But it's the best prediction. So this is the point of the best fit line, is for predictions. Okay, and the question is, how do we come up with the best fit line? So we're not going to do this example here because we're not all together and whatnot. But what this example is coming up with a relationship between a person's hand span, how far it is from the tip of your thumb to the tip of your pinky, on the same hand, of course, not two different hands. And we want to use that as a prediction for how tall the person is going to be. Do we expect, as a general rule, that the larger the hand span, the taller the person? Do we expect that relationship to be true? Right? We certainly expect that relationship to be true, right? And
Yeah.
this is the data that we have. This is hand span.
Yes.
Thank you, Angela, for jumping in. It's so sweet that you were there to
I agree with Angela.
yes.
It's that class participation.
Yes, exactly. Okay. Next thing I know, she'll be telling us what happened 10 minutes ago in class. But anyway, so we do expect that as the hand span increases, the height increases, much like this example, whereas the forearm length increases, the height increases. And suppose we think it's linear. So we plot it and we say, yeah, it looks linear. So we come up with the best fit line, and then we use that line to make predictions. Okay. In this example, which we're not going to do, but in this example, suppose it was shown that the best fit line had this equation. Suppose it was shown that the best fit line had this equation. How do I, there we go. Suppose it was somehow shown using calculus that the best fit line satisfies that if we know the height of the person, this is actually going backwards. It's using height to predict handspan, not handspan to predict height. But if we knew the height of the person, we can multiply that by 0.4, add it to -5.6, and that would give me the predicted handspan. So what handspan does the equation predict for a height of 68 inches? You would just plug in 68 into the height. So 0.4 times 68 and -5.6 plus that. Let's go ahead and do it.
Why 0.4? Did I miss something? I'm sorry.
Yes, because yes, behind the scenes, it was somehow determined that this is the equation without telling us where it came from. So if I plug in 68, that would give me a 21.6 inch or centimeter, whatever the units are, prediction of the handspan. Okay. This is what we use the best fit line for predictions. Where did this come from? They're not telling us. That's beyond the level of the course. It came from calculus, but we can use it to predict. Okay, with the purpose of the best fit line predicts. So this one says graph the regression line on the plots. Okay, well, what we need is 2 points. Let's plug in 74. When I plug in 74 into my equation, what do I get? When I plug in 74 into my equation, what do I get?
Negative. Oh.
No, go, Lori.
Too late.
No, I think you're right because here.
No, you do it.
I get 24.
24.
Sorry,
Okay.
No,
that's not what I got. That's not what I got.
Well, Lori,
But -5.6.
plus
Oh.
0.4 times 74. You got to do the multiplication.
29.6. I got that. Yeah, and then okay, sorry.
Okay.
You're right.
Now let's plug in another number like
A
62.
little slow.
Let's plug in 62.
$19.2.
19.2. Yay.
19.2, which is about here or so. So my best fit line, because my best fit line has to have those two on it, this would be my best fit line.
That sounds like a band name or something.
The best fit line?
Best fit line.
I think that'll be a great name for a band. Coming soon to a theater near you, the best fit line.
Opening
Okay.
for the Ramones, the best fit line.
Sounds like Chippendales or something.
Oh,
The best fit line. Okay, so here we have the equation of, so here we have the line. Now, does that seem like a reasonable best fit line based upon the data? I'm not saying it's correct, but they're saying it's correct. But does that seem reasonable? Right? We certainly see a slight upward trend. It kind of has
It
half the
seems
points
reasonable,
above, half the
yes.
points below. It's fairly reasonable. It's fairly reasonable. In fact, it's correct according to them. So it certainly is reasonable. Would you say that this is strong, moderate, or weak?
moderate.
Moderate at best, I would say. Maybe even weak, but moderate at best. Okay, so let's now keep going, and try to come up with some rationales. Oh, well, let's actually just not keep going yet because I want to introduce something else. So if I look back at that, best fit line, so that tells me that somebody 74 inches tall should have a hand span that's 24 centimeters, correct? That's what the best fit line is predicting. Will you agree? Yeah, if you're 74 inches tall,
Yes.
it predicts 24. But
I agree.
but we actually have someone in our data that is 74 inches tall. Right? We actually have someone who is 74 inches tall. Was their hand span 24 inches?
Almost.
But
Oh,
was it? Was it 24 inches?
No.
No.
it looks like 23 or
It
whatever.
looks like 23 inches, correct? So this here is the actual. That's the actual. That's what you actually have as your data, the actual. And this here is the predicted. This here is the predicted. So we define the residual. We define the residual or the error in prediction, but I will use the term residual as actual minus predicted. We use the letter Y for actual, and we use Y with a little hat on top, Y hat for predicted. In our case, the actual was 23. The predicted was 24. So our residual is -1. Our residual is -1. The actual was 23. The predicted is 24. So the residual would be -1. Anything that's below the best fit line has a negative residual. And anything that's above the best fit line has a positive residual. So all the points above have positive residuals and all the points below have negative residuals. Does that make sense so far? So what we're going to do is now start working towards finding the best fit line. So here we have a situation of 4 data points. We have 2, 3, 2, 7, 8, 5, and 8, 13. A student suggests that the best summary line is the one that goes through the most points. Does that seem reasonable? That the best line is the one that goes through the most points? Well, let's think about it. That goes through 2. That goes through 2. That goes through 2. That goes through 2. That almost goes through 2, but my graph was off. Oh yeah, I fixed it. That goes through 2. That goes through 2. There's lots of lines that go through 2. Are you going to claim all of them are the best one? That doesn't make any sense. So the first option of, oh, it's the one that goes through the most points, we shoot that one down. We tell the student, no, you're wrong. That's nonsense. Think a little better. So the student goes on and says, okay, fine. How about the one that has half of the points on one side and half of the points on the other side? Is that a good one? Well, let's think about it. That has 2 on each side. 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 There's lots of ones that have 2 on each side. So what would you say to the student about that one? You say, right? We have 2 X's. We're almost out. 3 X's and we're done, right? 2 down. So a third student suggests, he goes, okay, how about this one? Let's make the residuals as small as possible. This thing that we just decided upon, the difference between actual and predicted, the residual, Let's minimize the sum of the absolute values of the residuals. Let's minimize, make as small as possible, the sum of the absolute values of the residuals. In other words, this guy right here. Take each residual, add them together. Oh, sorry, take each residual, absolute value them, and add them together. When you do that, you will get a number. A different line would give you a different number. So out of all the lines in existence, pick the one that gives you the smallest value for that. What do you think about that idea? Look at every line in existence and take the one whose sum of absolute residuals is as small as possible. What do you think about that idea? What do you think about that idea? Take the one that makes the sum of the residuals or the absolute values as small as possible. Well, here's what I'm going to do. I'm going to try it. Let's draw a line and calculate that. So what I'm going to do here is I'm going to draw a line that looks like this. That's a horrible line, so ignore that. I hit the wrong button. I'm going to draw a line that looks like that. So let's calculate the residuals here. We have 4 points. Each point has a different residual. So what's the residual for this point? What's the difference between its actual value and its predicted value, which is what the line gives? Its actual value is 7. Its predicted value is 3. So what is its residual?
4.
4. So this one has a residual of 4. This one is on the line. So its actual and its predicted are the same. So what's its residual?
3.
No, it's on the line. So its actual and its predicted are the same.
Oh, 0.
So the residual is 0. This one's on the line. So what's its residual going to be? 0. This one's beneath the line. So what's its residual going to be?
Negative.
It is negative. So its actual is 5.
Negative 5.
And its predicted is 13. So it's going to be negative 8. All right. And therefore, if I take the absolute values of those 4 numbers and add them all together, what do I get?
28. Oh, wait.
Take the absolute values of those 4 numbers. What's the absolute value of 4?
4.
Absolute value of 0.
0.
Absolute value of the other 0.
0.
Absolute value of negative 8.
8.
Add them together. What do you get?
25.
Uh,
They
4
did that wrong.
4 plus 0
12.
plus 0 plus 8 is 12.
I thought we had 13 in there. Oh, that was the predicted. Sorry. I bet.
Okay, so that's option number 1. We get 12 for this value. Now I'm going to give a completely different line. I'm going to give that line. So let's compute this one's sum of the residuals. This point here lies on the line. So what is its residual?
0.
This one here, the actual point is 3, but the predicted is 7. So what is its residual? Negative 4.
Negative 4.
This one's on the line, 0. And this one is 8 above 8. So what does option 2 give?
12.
Also gives
I'm sorry.
12. Yeah, also gives 12, right? We absolute value them and we add also.
Okay, it's absolute value. Yeah.
So we got to shoot this one down too, because we see different lines that are completely different can have the same value for this. So that didn't work either. Right? We shoot that. That's the best one yet, right? It's the most mathematical, but we still shoot it down. Can I erase? Okay. So we move on and we try something new. Of course, the last one reminds us of the MAD, right? If you look at the formula for the MAD, it's very similar, correct? Okay. But once again, let's do one more example. If I do this one, which looks like this, and I actually write out all the possibilities here. So the first point here, which is 2, 3, what is its predicted value? What does a line tell me I should get for an X value of 2? Go up, down to the
3.
line.
3.
No, the line, well, the predicted is 5. The actual is 3. This is what I actually got. The line says I should get a 5.
Oh, yeah.
When the actual is 7, the line says I should get a 5. When I get 8, the actual is 5, but the line says I should get a 9. This one here, the actual is 13, but the line says I should get a 9. So what is my actual minus predicted for the first one? It's -2. 7 minus 5 is +2. 5 minus 9 is -4. 13 minus 9 is +4. When I absolute value these and I add them all together, what do I get? Who do we
12.
appreciate? I get 12. So once again, we have a situation of another line that gives us the same value. So once again, we see that this is not working. Okay. Once again, we see it's not working. And here's another example. This is one of the ones that we did that again gives us 12. Okay. So the next guess is to do as follows. We do again the same thing as before. We take the predicted. We calculate the residuals just like we did before. But here we'll do something different. Instead of taking the absolute value and adding them, we're going to square them and add them. So let's go back to our line. Let's do this one first. Okay, what's the residual? What's the actual for both of these? The actual for this one is 3, right? The actual for this one is 3. But what's the predicted? 7, correct? Yes, you with me, please, everyone?
Yeah. Actual 3, predicted is 7.
Okay, the next one had an actual of 7 and a prediction of 7. So that one goes here. The next one, the 8, had an actual of 5 and a actual of 13, but both of them have a prediction of 5. So we're going to go here to them and we're going to put in 5s. This gives us 3 minus 7 is -4, whose square is 16. 7 minus 7 is 0, whose square is 0. 5 minus 5 is 0, whose square is 0. And 13 minus 5 is 8, whose square is 64. So when I take these numbers and I add them, these squares, what do I get?
Let's see. 80.
80. This gives me 80. Okay, this gives me 80. But let's go back and consider the other line that I had, which went up this way. The one that I did, I erased it, of course. But the one that I did that looked like this. Oh, the one that I did. That
Question.
looked like that.
Can I ask you which video this is? I mean, what,
16.
16. No, but what is the lecture number?
Oh, I
Doesn't
won't know.
coincide.
If
23. The Monday, Wednesday one said 23.
Yeah,
23,
but,
thank you.
but we missed a class. We missed 2 classes now. So this.
But I can go back and watch the other class number 23, right?
Yeah, you should. You can maybe watch it twice. Yeah, that should work. Okay. But if I go here and do this one, which I think might be the best, so let's remind ourselves. We had 5, 5 for my predicted, and 9, 9 for my predicted, right? 5, 5, and 9, 9. So let's go to the other one. And let's put in 5, 5, and 9, 9 for my predicted for those and my predicted for those. So -2, whose square is 4, +2, whose square is 4, -4, whose square is 16, and +4, whose square is 16. And when I add them, what do I get? When I add them, what do I get? I get 40, which is a much smaller number than this one. And yes, this is the way we do it. We find the line that makes the sum of the squares of the residuals as small as possible. That is the mathematical approach. And it's called, for that reason, the least squares regression line, okay? Because it makes the sum of squares as small as possible. The least squares regression line. Okay.
So basically what you're saying is that we have to continue making lines until we get it to as small as possible?
So you would think that. You would think that. But here's the thing. That sounds like a daunting task because you can make lines for hours. How do you know that you're ever going to reach the point where it's as small as possible? How do you know that you didn't miss one and there's one even better and smaller? Right? The answer is that's not how we do it. The calculus approach manages to look at every single possible one and pick out the one that does the job for us. It's almost magical in how it works, but unfortunately, I can't go into the details because this is not a calculus-based class.
Okay, so my question is, so if we're given the line, we just do what we did, but then how do we get the second line that makes it smaller? I didn't quite understand.
No. So what we just did just now is we just examined a few different lines and saw that a lot of the stuff that we did earlier gave us the same value, but this one gives us a unique answer.
Unique means what?
Unique means they're not all the same. It's different. Like the last one we had 12, 12, 12, 12 for all the different cases, right? We weren't able to distinguish the best one because they were all 12. This technique does distinguish the best one. Okay, it gives us the best one by giving us the one whose number here is as small as possible. Your question is, how do I determine that it's a small? Maybe there's another line that I didn't find that I didn't try. How do I know that I found the one that's as small as possible? What I'm saying is you can't without calculus. It's a calculus technique. This is just conceptually telling you that the one that makes this as small as possible is the best one. And if you can somehow figure out a method that you can find that, you know you got it. And that technique exists. It is calculus. And hopefully one of these days you all realize that math is like the greatest thing on the planet. And you all want to just do more math and more math and more math. And because of that, you'll all switch to become math majors. It'll be great. You can all thank me for that. But until then, we're just going to keep going forward. So,
I'm sorry, Professor, just to try to get some kind of like,
I'm
what is
listening.
the purpose of this? Like, if you're looking for the smallest line, is that like use something?
Not the smallest line. Again, you're looking for the least squares line. The least squares line is the one that minimizes the sum of the squares of the residuals. Out of all of the infinitely many lines in existence, it is the one and only one that will make the sum of the squares of the residuals as small as possible. If you can,
is that used in like engineering or something, or what do they need that for?
Everywhere.
Everywhere.
Any statistical analysis will have a regression section.
Because you're trying to make the most accurate predictions.
100%. Yes. Okay.
So you try to eliminate all this all over the place just to try to get more of a whatever. Anyways.
No, what's your question? What's your question?
It's deep. No, that's okay. I think I'm just trying to like figure out and what's the application of, or what is this building towards?
So
Not for us in this class, I know.
yeah, no,
but
it's building to, well,
what is this like the basis for? It's for
well, this is
doing
the basis for
calculus.
this is the basis for statistical analysis. I mean, least
Oh.
squared lines are I mean, they're. Hold on, give me 1 second. I have a book here. Oh, wait. So, fascinating book. Regression analysis. Entire book about regression and its importance and the math behind it and the theory and how it works and applications and just a lot of great math out there. You guys are just skimming the surface. I know you're not all math people. I know that, but you know, it's
I have
amazing.
a math major son, but he never wants to talk to me about math.
Well, that's a shame. That's a shame. All right. So this is okay. So let's say we've established that this is the best fit line. What is the equation of this line? How do I find the equation of a best fit line? Who remembers how to find the equation of a line? Well, you need 2 points on the line. We have this
X and
point right
Y.
here. What's this point right here?
That's the Y. Oh, it's a
2,
3 and
well,
2.
2,5.
Oh, 2,5.
And this point here is 8,9,
8,9.
right? 8,9. Correct? Yes, no, maybe so?
Correct. Correct.
8,9. So the slope is what? Slope is rise over run.
Rise
I
over.
rise from 5 to 9. So I rise up by 4 as I run from 2 to 8, as I run 6.
The actual formula is y1 minus y2 divided by x1 minus x2.
That is 100% correct. Y1 minus Y2 divided by X1 minus X2. 100%.
Get it, David?
Yes.
Look at you, mathematician.
Leaving
the
us
other
in
way
the
around.
dust.
Or the other way around. That's correct. Because what you label as 1 and what you label as 2 is the same. You know, who cares? You are 100% correct. So slope is 2/3. So the equation of the line is y minus the y value of one of the points, so y minus 5, equals the slope times parentheses x minus the x value, x minus 2. This is what's called the point slope form of a line. Hopefully you're all familiar with point slope form of a line, which I can write out as y equals 2/3 x minus 4/3 plus 5, so plus 11/3. Okay, so this is the equation of the line. As they say in Hebrew, it's muy importante. Right, so y equals 2/3 x plus 11/3. That is the equation of the line. Okay, I'm going to erase some of this other stuff, but I'm going to keep the line. So watch this. What is the average of the x's? What is x bar equal to in this example? What is the average of the x's?
5.
5, good. And what is the average of the y's?
28 divided by 4 is 7.
Excellent, Laura, you're knocking it out of the park.
Oh, geez, if this could just get me through this class.
Well, I'm here to get you through the class, Lori.
Okay, good.
So x bar equals 5 and y bar equals 7. If you plug x bar into here, what do you get out? Go ahead and try that. And hopefully this is my lunch coming because I'm hungry.
What are we having today?
We're having penne pasta.
No, we're
No,
having soup.
we're having soup.
The pasta's later.
Pasta's later.
Let me put it.
Oh,
Okay.
nice.
Thank you, Father.
Thanks, Dad.
Hey.
Go
Anytime.
anytime.
It's the least I can do.
It's the most you can do.
At this point, yeah.
So I plug an X bar into my equation. What do I get?
7.
You get 7. In other words, if X bar goes in, Y bar comes out, which means the average of the X's and the average of the Y's, that point, X bar, Y bar, must fall on the best fit line,
It's magic.
which means if you're trying to construct the best fit line by hand, first find X bar, Y bar, that gives you a point, and then make the line to the point and just tilt it until you feel you have the best point. But you know that X bar, Y bar must go on the line. Someone, a couple of texts here. Who we got? We got hello. Well, that doesn't really do anything. Good job, Arps. You're doing great. Thanks, Pat.
I have a question.
Yeah.
How did you get x bar equals 5 and x bar equals y? 7.
Well, add the X's and divide by 4. What do you get?
Okay. I just wanted to know how you got it. Okay.
And that's how I did it.
And the y.
And the Y, same thing. Same thing. Same thing. Okay. So let's just review slope for a second. Y equals 3x minus 8. What's the slope of that line?
3.
3. That's a number in front of the X. Y equals 5 minus 0.3x. What's the slope?
0.3.
Try again.
5.
No, it's not the number by itself.
Oh,
It's the number in front of the X. What's the slope?
Negative 0.3.
Negative 0.3. And the last one, Y equals 15.6x plus 18.4. What's the slope?
15.6.
15.6. The slope is always the coefficient of X. It's always a number in front of the X. Even if I switch the order that I'm writing them, it's always the coefficient in front of the X, or slope is rise over the line. So in this case, that equation that we started the day with, what's the slope there? I love math. Someone said, what? What? Angela, you love math? That's amazing.
Because you're good at it, Angela. That's awesome.
So are you, Lori. What are you
Oh,
talking about?
thanks. I just need all the help. When I was doing that exam, like I just get nervous.
Well,
Just
everyone
full
gets nervous.
disclosure. So
I won't
hard.
tell any, Laura, your secret is safe with me and everyone else in the class and everyone who ever leaves the class and talks to other people. So
Oh, I'm
hopefully it won't get out there. So,
yeah.
so what is the slope of this line here?
2/3.
2/3. No, not our line. Sorry, let me erase that. Sorry, that's not what we're doing now. It's this problem here. Here's my equation. Hand span, which is my Y value, is negative 5.6 plus 0.4 times height, which is my X value. So what's the slope?
Negative 5.6.
Try again.
Wait, what?
What?
I'm sorry. Never mind.
No, don't go away. Remember, the slope is always a number attached to the variable. What's the variable here?
0.0.
And what's a variable? What's the X variable?
The height.
The height.
Oh, the height, yeah.
So what number is attached to the height?
0.4.
He said it.
0.4. So that means that the slope is 0.4. Interpret the slope. What does that mean? The slope is 0.4. What does that mean in the context of this problem?
In the context of this problem,
Yes, don't just say, oh, the slope is 0.4. What does that mean?
it's going up from the, no, never mind. I forgot how to verbalize that. What page is that, Professor? Oh, interpreting the slope. Here we go.
So it means as follows. Remember what slope is. Slope is rise over
It's
run.
overrun.
So 0.4 is the rise over the run. What that means is if I move 1 unit this way, I will move 0.4 units this way. Because 0.4 is 0.4 over 1.
Over
Rise
one.
over
There
run.
you go.
So for every height increase of 1 inch, I expect a handspan increase of how much?
0.4 over 1.
Or 0.4 centimeters.
Or yeah, 0.4.
For every 1 to the right, I expect to move up 0.4. So for every 1 inch height increase, my handspan will increase on average, or my predicted handspan increase will be 0.4 centimeters. That is the interpretation of the slope.
Uh-huh.
Okay, don't yawn in my class.
I'm sorry, that was so rude.
Okay,
Apologize.
I forgive you. In this example, what's the slope?
Negative
Negative what?
1/2. -5. I'm sorry, -5 over 1.
Well, negative 5 over
Negative
what?
0.5 over, well,
Negative 0.5.
negative 1/2, yeah.
Negative 1/2. Somewhat moderate math, moderate correlation. R is negative 0.66. Each point on the scatter plot represents one person, because remember what this is. This is the relationship between the CMUS score and the Wyatt 2 math composite score. What are these? There's math achievement and math anxiety. The scatter plot shows the results from 2nd and 3rd graders. This is a higher math achievement, and this is a higher math anxiety. As people have more math anxiety, their math scores drop it apparently, huh?
Yeah, I'll attest to that.
And so the only way to overcome math anxiety is to get better at math. If I asked you what is 1 + 1, anxiety would never kick in and say, oh, I can't do it. No, because you know it, you've internalized it, you have it down. Math anxiety comes when you don't know it well. So you get nervous. And then that nervousness makes it harder to do math well, right? But if you truly have internalized something and you know it well, you can't get nervous. 1 + 1, we all know the answer, right? Now, that takes a lot
3.
of time to do that. So we don't always have the time, but in theory we could. Now, the question is, what does the slope mean, negative 0.5? In the context of this problem, what does negative 0.5 slope represent?
Going down.
No, more specifically.
More specifically, the hand span. What?
Half-band problem's over. This is a new problem.
Oh, the scores are
So-
going down with the more anxiety.
So give me a very specific quantitative correlation.
Well, the quantitative correlation of this problem. No.
Hey, you were doing great. Even though you were just being a little sarcastic, but that's okay.
Is it?
I volunteer. Oh,
Angela!
no.
Yay, go.
No. I don't know who was talking, but they can go.
That was Yesenia was talking.
Lies.
What do you got, Yesenia? Say it.
Go for it.
I've got nothing. My answer is Angela.
Wow. Okay. Okay. Angela, you're on point. Go for it.
Okay, so the slope is rise over run. So as anxiety scores go up, the maths achievement scores will negatively go down 0.5.
So as the anxiety scores go up by how much?
By 1.
By
Anxiety
1.
scores or math scores will decrease by 0.5.
That was awesome.
Angela, you
was
need to answer my text message now, okay?
And that was perfect. So if someone's math anxiety score is 20 points higher, how would that predict their math achievement would compare? Based upon what you just said, if their actual anxiety score was 20 points higher, how would that, what would that do for their math score?
It's gonna, do you multiply the 0.5 times 20? No.
Yes.
Would it go down 10
Yes.
points?
Yes. All hail Laurie, the math queen. Exactly. Beautiful, 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 beautiful.
There's hope. No, just kidding.
Always hope. There's always hope. And we're not going to do the end. So that's it for this chapter. Is there any question on it?
What is life? Oh, that not that.
What is
Okay.
life?
Sorry.
Unfortunately, I am not someone who can answer that question because, you know, like most adults, mine sucks. But I'm sure you guys are all familiar with this.
Your life doesn't suck, Professor. You're giving back to society by teaching. Your life doesn't suck.
That's very sweet of you to say.
No, you're giving back.
I
It's
feel I'm doing my part.
You are.
I feel I'm doing my part.
Especially with these STEM subjects. Keep it going.
Okay, I'll try. Okay, I'm going to stop sharing now. Are there any questions on what we did today? Other than life, which I can't really answer.
I have one question. It's a little unrelated though.
Oh, okay. That sounds interesting. Go ahead.
What were you eating earlier? What was your snack?
I mean, my meal was
Yeah. Staring it up, whatever it is.
a bowl of chicken soup.
Yummy. Also, Lori, your hair looks so pretty.
Oh my gosh, thank you. It's so funny because my husband and I are getting our pictures taken on Saturday. So I have to like try to put some kind of curl in there like 2 or 3 days before. So it comes down like a not big Texas hair. So thank you. I'm not trying to do it. It's,
Fun fact, Patty loves Texas. I'm sure she would like to say something.
Go Longhorns.
I hate talking about hair. So let's not do it.
Just because you don't have any.
Oh, I have look at all this. Okay. What's all this, huh?
You do realize we're still recording, right?
Oh, yeah. What could it?
That's on the internet.
That's now going to be on the internet forever.